Till now we have seen method of solving separable ODE. Now we'll see method of solving another class of first order ODE. So for this we introduce a homogeneous function, a function on n variable, a function f on n variable x1, x2, x3 up to xn is called homogeneous if f of tx1 comma dot 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 txn is equal to td f of x1 comma dot 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 xn for some d belonging to z and for all t not equal to 0. So what is happening here is the t, when multiplied to each of the variable of this function f, the t will come out, if the t comes out with the power of d and gets multiplied to this f x1, x2, xn, then such a function is called homogeneous function. If any function satisfies this relation, then it's called a homogeneous function. And if it comes with a power d, then we'll say d is the degree of homogeneity of the function f x1, x2, x3 up to xn. We see an example. Suppose f is a function of two variables x and y. It is given by x square plus xy plus y square. You can easily see that this is homogeneous of degree 2, because if you substitute tx and ty in place of x and y, then it will be tx square, then it will be tx times ty, and here will be ty whole square. So from each of this term, t square term comes out common, and so we get f of tx comma ty is equal to t square f of xy. So the value of d here is 2. So this is homogeneous of degree 2. We look at yet another example. fxy is equal to y plus x cos square of y by x. Pause for a minute and guess what is the degree of homogeneity of this particular expression. First of all, you observe that this is homogeneous. So you must have realized that when you put tx here and ty here, then here we get ty, here you get tx, and here it will be ty by tx, the t will cancel. So it is, you can take t common from here and here, so it will be t times f of x comma y. So the degree of homogeneity here is 1. Now we know when a function is homogeneous of degree d. Now a differential equation, a first order ODE, which can be written as m of x comma y plus n x comma y dy by dx equal to 0, where m is a function of two variable, n is a function of two variable. Such a differential equation is called homogeneous if m and n are homogeneous of equal degree. That means I have defined in the previous slide what is a homogeneous function. So here m needs to be homogeneous, n needs to be homogeneous, and so m will be having some degree of homogeneity, n will have some degree of homogeneity. That degree should be equal. Then this first order ODE is called homogeneous first order ODE. So if you have a homogeneous first order ODE, then we can solve it by a method that I'm going to explain now. Look at this example. Here mxy is 2xy and nxy is y square minus x square. So what is the degree of homogeneity of mxy? You can clearly see that the degree of homogeneity of mxy is 2, And what is the degree of homogeneity of nxy? The degree of homogeneity of nxy is again 2. So since both mxy and nxy have same degree of homogeneity, namely 2, this is a homogeneous ODE. So now we describe a method of solving homogeneous ODEs. Suppose we are given homogeneous ODE, first order ODE, that is the differential equation is m of x comma y plus nx comma y dy by dx is equal to 0, where m and n are homogeneous of degree d. Then what we do is we define v to be equal to y by x. Now we take so we write y is equal to vx. When we write y is equal to vx and take derivative, we'll get dy by dx is equal to v plus x times dv by dx. So we are differentiating this quantity by transferring x on the right hand side. Then we get this particular expression. So what we do is, in this particular given differential equation, we replace dy by dx by this quantity and we replace y by vx. So we get this expression m x comma xy. We got this from this particular differential equation, m x comma xv plus n x comma xv times in bracket x dv by dx plus v bracket close is equal to 0. Now we know that these are of have the both m and n have the are homogeneous of degree d. So this x comes out from the variables of m and variables of n with the power d. So it is xd times m 1 comma v plus xd times n 1 comma v multiplied with x dv by dx plus v bracket close is equal to 0. So here we assume x is not equal to 0. So we cancel xt and then we have this particular expression. So if we cancel xt, we get this expression. This we rewrite in the next page the following. So xd has been cancelled here. This is what we get. You see, this bracket we have opened now. So n1v gets multiplied to this and n1v gets multiplied to this. So n1v appears 2 times here. Now this expression is in a form that we already know. This is a separable ODE. In the variable v and the variable x, this is a separable ODE. So the given equation here, we can multiply this equation by suitable quantity and rearrange the term so as to get all the terms related to x, all the terms related to the variable x together and all the terms related to the variable v together. So we have rewritten the expression or the differential equation which is appearing here in this particular form, and you can see that this is a separable ODE in the variable x and variable v. So we know how to solve separable ODEs, so we can solve this differential equation. So this method we are going to use to solve homogeneous ODEs. Before that, there is a remark. The remark is that it is important for the above method to work is that the ODE we should be able to put in the form where y dash is equal to f of y by x. What is that we want? Y dash is equal to f of y by x. So this is the same thing that we happened in the previous slides. What we want? Y dash is equal to f of y by x. So this quantity, if you know, if you check, this quantity is dy by dx, that is y dash. So this is y dash. And if you cancel xt from here, then you can actually write this y dash completely in terms of m1 comma v and n1 comma v. You transfer it to suitable side and you get that. So m1 comma v and n1 comma v is function only in variable v. And what is v? V is y by x. So we have been able to write y dash is equal to sum f of v or sum f of y by x. So for the above method to work, we should be able to write our differential equation in the form y dash is equal to f of y by x. Now we'll see example. So this particular example is a homogeneous ODE. We had checked in this case both mxy and nxy are homogeneous of degree 2. So we know the method. Here we have to substitute y by vx. That is same as taking v to be equal to y by x. Now we differentiate this with respect to x. What we get, dy by dx is equal to v plus x times dv by dx. That is what was illustrated in the previous slide. So what we have to do, we have to replace dy by dx by this particular expression, and we have to replace y by vx. So when you do that, the given ODE can be written in this form. And here, assuming that x is not equal to 0, we can cancel the x squared term from this entire expression, and this is how it looks. Now this is in fact a separable ODE in terms of x and v. You rearrange the terms by multiplying by suitable quantities and taking all the x and v's together. So you simplify first in this form and then you separate the quantities. So you see clearly here all the variables have been separated, and so you can integrate this. So the integration of this particular quantity appearing here is ln of mod x, and this particular quantity that is appearing here, you can do partial fractions and you can get this expression. Once you have converted this into this expression, then you can easily integrate this. So you can see the quantity on the numerator is a derivative of the quantity in the denominator. So both this quantity, this particular thing's integration is also in terms of log, and this quantity is also in terms of log. So you have log mod x plus log of L square plus 1 minus log of mod v. So by ln I mean log to the base e, and this quantity is equal to integration constant c1. So you can rewrite it as x times v square plus 1 divided by v is equal to some constant. So for our convenience, we took the constant to be equal to 2c. So you have understood this. Because it is in log, we can multiply all the quantities here, and minus means we can divide the quantity inside the logarithm, and so this will come from exponential, and so I replace this constant by its exponential, and we introduce the quantity 2 with a purpose. The purpose being what you will see below, that we can write it as circles if we introduce this quantity 2 here. So now you substitute v by y by x. So here you have y square by x square in this side, this and here you will have y by x. So when you multiply these things, this is the final quantity that you get. Now you can complete the squares. So you have x square here, and then this you can bring inside on the left hand side. So you will get y minus c square, and this would need one more c square. So this is how it looks like. So this is the solution of the homogeneous ODE that was given in this slide. So here are some more exercises. So solve 4x plus 2y plus 5 whole quantity in bracket times y dash plus 2x plus y minus 1 whole thing in bracket is equal to 0. So how will you solve this? You can pause the video and try to solve it yourself. You may have already observed that you can take this quantity 2x plus y equal to some variable v. Then the quantity that is appearing here is 2 times v. And once you replace this by 2v and v here, then it will reduce to a form which you can solve. It will be a variable separable ODE, or variables can be separated. And separable, once you get a separable ODE, you can solve it. And then at the end, you substitute back the value of v. So you should be able to do it. Now I look at the next problem. Here y dash is equal to, in the numerator, x plus y minus 3, and denominator x minus y minus 1. So you can pause the video and try to solve this on your own. So you must have observed that there is a difference between this particular type of problem and the problem appearing in question number 1. In the question number 1, if you take this as v, then this is just 2 times v. But the same thing, if you take x plus y as v, you cannot have it as a multiple of v here. So we have to use some other technique to solve this problem. The technique that we use to solve this problem is we convert this into a homogeneous ODE. So the trick that we use to convert this into a homogeneous ODE is that we do change of coordinates. So what do we mean by that? We substitute, we replace x by x1 plus h, and we replace y by y1 plus k. So x1 and y1 are again two variables, and h and k are some fixed numbers. We have to determine those numbers in a suitable way so that this becomes a homogeneous ODE. So we just replace the quantities here. So you will notice that dy by dx is same as dy1 by dx1, because this is a linear translation. The variables have been changed by linear quantity. It has been changed linearly. So dy by dx can be replaced by dy1 by dx1, and that is equal to, you replace x by x1 plus h, you replace y by y1 plus k, and minus 3 appears here, and same thing below. Now here what we do is we choose h and k such that the quantity that is appearing here, h plus k minus 3, that becomes equal to 0, and the quantity that is appearing here, h minus k minus 1, that becomes equal to 0. So we have two systems of linear equations appearing here. So we solve this system of linear equation to get the value of h and k, and so basically we have to translate x by those value of h and k and then rewrite the equation. So what will happen here is, once you find the h and k, then for this value of h and k, we actually, because we have this and this to be 0, so this looks like dy1 by dx1 is equal to x1 plus y1 divided by x1 minus y1. So what I just now said, that if you have zeros here, so this particular equation is a homogeneous equation. And so you can apply the method of solving homogeneous equation that we have described in the previous slide. So this is an exercise you can do, and you can check the solution comes out to be this: e raised to tan inverse of, in bracket, y minus 1 divided by x minus 2 is equal to c times square root of x minus 2 whole square plus y minus 2 whole square.